Good afternoon, student of the course 4006. Today we're going to be talking a little bit about truncation error versus error bound. There's some kind of confusion between the two, and basically they use the same formula. So let's do an example, and we gonna get this straight. Like for example, let's say that the problem is, let's see, oh, here we go. Calculate the truncation, oops, truncation, this is, I'm using like the truncation error and the error bound for the trapezoidal rule for, let's say that we want to integrate dx over x between limit 1 and 2, and are we gonna be doing this, let's say, since we're gonna using a numerical integration, sort of like a numeric method, then we're gonna establish that n equal 4, right? And that will do. So basically what we going to do is like the function here, if I f of x in this case is 1 over x, and if you do quickly a plot of that, will look like this. As x get bigger, then 1 over x gets smaller, and so forth. So this is sort of like the behavior of what to expect. Now n is going to be 4, so that means between, let's say, 1, sorry for this, between 1, let's say, and 2, so we want the area of this is the area that we are interested, and we're going to divide this within 4 trapezium. There we go, 1, 2, 3, and 4, and that's basically it. So if we want to get, like for example, here clearly said the truncation error. Well, the truncation error by definition is basically ET, truncation error, equal to the real area. Let me put it this way, like for example 1 to 2 dx over x, right? That minus the area calculated by the trapezoidal rule. All right, so if we do that, then we will be able to calculate the truncation error. In fact, if you do an expansion in the Taylor series, you will get an approximate error number, or approximate truncation error that will look like this. It's going to be equal to, let me put this right here, minus b minus a to the cube divided by 12 n squared. All right, and that multiply by the second derivative of f, but this is an average value, and that where the confusion might start. this here. How you get this value here, the average of the second derivative of epsilon, where epsilon is a number between a and b. All right. So if we want to do either, basically this is an approximation of this part here of ET. Let's put it like this. Well, actually, better than that. Let's put it like this. That this is an approximation of this, and this can be, you can use this formula to get an approximate truncation error using the trapezoidal rule. Now, let's start with, let's do this first. So let's do the actual integration. You know, obviously the idea of using numerical method is because one you don't know how to do this, but let's say that we know. It's because what we are interested is in getting the truncation error. So let's say that we know how to integrate that. So the real integration will be 1 to dx over x. If you check an integration table, you quickly discover that this is basically by definition log of x. Now we need to evaluate that between 1 and 2. So basically you have log of 2 minus log of 1. Obviously log of 1 is 0. So you will end that the real integration of this is log of 2. That's the true value, the real value. Now, to get the truncation error, we need to get the actual value using the trapezoidal rule for n equal 4, because that's what we start the problem. Calculate the truncation error and the error bound for the trapezoidal rule for this integral for n equal 4. All right, in where f of x here, as shown here, is 1 over x. So let's do that. So the area by using the trapezoidal rule, I'm gonna put here basically the formula how it looks like, just in case you might have forgotten. Is f of a, that's this limit here, plus 2 times the sum of all intermediate value to n minus 1, and here is for e equal 1, and that plus f of b, and that's it. So one easy way to do this application of this formula here for trapezium, or the trapezoidal rule, is just to do a table. And within the table, you start, let's say, with x, f of x, and now let's say that we start at the lowest limit, that's 1. Now we need delta x so that we increase this value until we get to finally to the value of 2. So let's do that. What's the delta x for this? Let's write it here. Delta x by definition is b minus a over n. In this case, delta x is 2 minus 1 over 4. That's the value of n. That would be 1/4. So that would be 0.25, a quarter. So that's 1. This is 125. Keep adding. That's 1.5. Another one, 1.75. Finally, 1.75 plus 0.25 is 2. And we are done. So we are between 1 and 2. Here's the 1, here's the 2. So if you want to be sure, you have to have 4 boxes here. That will be 1, will be 2, will be 3, that will be 4. Excellent. Now, we need to calculate f of x. For example, we need f of a, but f of a, that would be 1 over 1, because remember that f of x is 1 over x. So this will be, the second one will be 1 over 1.25, the next one will be 1 over 1.5, and the other one 1 over 175, and the last one 1 over 2. We can evaluate here nearby to have those values. And now, one quick things. I like to add here that we are going to be using the trapezoidal rule. With that said, what I'm saying is that I'm applying this formula right here. So for example, f of a, we know that this is 1. So here in the trapezoidal rule, all this part here need to be added together like a big sum. So f of a, that would be 1. Now, whatever value I come out here, that will have to be multiplied by 2 because I need to sum all of them and then multiply by 2, which is the same as whatever is here, I multiply by 2, and so this one, and so this one. Careful here. The last one, which is obviously 0.5, that one needs to just the way it is. That stay the way it is, 0.5. See? So let me work out the numbers here. Let's see if I got it here. I don't, but this is very simple. This is what I'm gonna do. I don't have a calculator nearby, but I have, obviously, I can use Excel to do this nice and fancy. So let's copy this. Actually, a little bit more. Let's copy from here so I don't lose anything. Control copy. And let's go to Excel and let's do a paste somewhere here. Paste special. Let's use bitmap. A little bit big. I can reduce it to make it smaller. A little bit smaller. That will do. There we go. There we go. So, I mean, again, you can, like for example, if I want to use Excel just to do this integration very quickly. So A, we know that is 1. B, we know that is 2. Like for example, delta n. N, we said that was 4. And basically now delta x, oops, or dx is b minus a, and that divided by 4. That will do. Now we got x versus fx, which is basically, we start here with 1. Now this is the nice thing about doing this in Excel. You can use all the power of Excel to do this very quickly. Like for example, I know that I'm adding that delta x through all the numbers, so it's easy to get to the bottom of this. Is you see, I got one more. Just take it out, and that will do. So now here is simple as adding the formula, which was 1 over x. So that means 1 over this one. And now we do the same for the others. And here is the part that is you will benefit from Excel very quickly. Like for example, this is, let's say this is trapezoidal rule that I'm applying. You know, because there's Simpson 1/3, Simpson 3/8, Simpson composite, and so forth. So it's kind of nice that you know what you're doing. Trapezoidal rule. So here you just go the way it is, but now here is the one that you need to multiply by 2, and you do it. And since you did it there, you can do it right here. But remember, this one stay the same. Now, what's the area? Let's put it here. The area that we are talking here, the area will be the sum of all this number as established by the trapezoidal rule for n steps. So that would be sum of all of them. And now that multiply by, you just multiply that by delta x and divide it by 2. And let's see. Delta x and divided by 2. Let's see if I got everything right. Let me check here. 1.25. By 2, by 2, by 2. This one stay, and that's it. All right. So I got the number 0.69724, and that's basically the area using and that's the area using the trapezoidal rule. So now let's do if you remember, if I go back, I can certainly copy this number, but it would be better. You remember the area under the curve for this problem was basically log of 2, natural log of 2. So the area, the real area was of 2, natural log of 2. And we know that we are kind of close, but not that close, right? So let's see. The truncation error ends up being truncation error equal the difference between the real area minus this one. And that's where we are. So basically, negative 0.00388. We are close, but not that close, right? I mean, I don't know. It depends how much precision you want. At the 2 decimal places, definitely you are in good shape. At the third one, well, there's an error here, right? And so forth. But, I mean, only with a value of 4, of n equal 4, we were able to get pretty, I would say, pretty decent, kind of a small error. Now, that was truncation error. Now, let's calculate what really means the error bound. Okay, error bound. Let's go back now to my OneNote. And so we did this. We did the first part, which is called the truncation error. And now let's calculate the error bound. For the error bound, let's move. This is the part that might confuse people. The error bound, let's say that we're going to take the absolute value of the error bound, gotta be, for example, less than or equal to b minus a to the cube 12n squared times, and here's the part, times the absolute value of the maximum value that you can get from your second derivative of epsilon, and that's it. Well, let's see if I reduce this a little bit. Okay, here we go. Yes, this is the error, the truncation error based on the average of the second derivative. If you want to do this, you know, by formula or calculation, versus if you want to do this by this, which will be an exact, pretty much an exact value. But if you know the integral value, if you know how to integrate this or your function, no problem. You subtract the value that you get from your application of your numeric integration method, and that will do. But if you want to use a formula, then that would be the formula for to approximate the truncation error. Now, error bound, don't use this average value. Use the maximum of the second derivative of the function. What that really means. What is my function? Let's start with my function. F of x, I said that was 1 over x. So the first derivative of that will be, if I put this in this way, make more sense. So that would be minus 1 over x squared. See? Now, or I should leave it like this, make more sense. All right? So the second derivative of x, that will be minus, that will be minus 2. Whoops, where is here? Sorry, here. There we go. Minus 2. And then that would be minus minus, so that would be positive 2 x to the cube. And that will do. So, what we are asking to do here on this formula for the error bound is to locate that maximum of the function. In what range? Obviously, missing here is that the range that we are interested is between, sorry for the 0, it's not 0, here is 1. Actually, let's see what's the limit of the, see, yes, between 1 and 2, between 1 less equal 2. So I'm interested within those, within that range. So if I check this function, it's like if you make a plot of that function, the behavior is something like this. So what I'm asking to you is to locate that maximum value, and let's say that this is 1 and this is 2. As you can see, I can calculate this value easily here because that would be 2. 2 over 1 to the cube, that's 2. Now this one here, on the other hand, is 2 divided by a. This value here is 2 divided by a. So that would be 1/4, that would be 0.25. And any value in between will be less than these two here. So it's easy, in this case, to determine that the maximum value of the second derivative of epsilon within the region of epsilon less than 2 is equal to 2, right? So I got that value, so calculation of the error bound for this problem will be just plug the numbers by b minus a. That's 2 minus, let's put it this way, 2 minus 1 to the cube over 12n squared. I said that n is going to be 4, so this is 16. And the maximum value is 2. All right. Now, if I go to my Excel again, let's see. Well, actually, I can certainly do this right here, but I'd rather put everything within Excel so I know we keep, track of what we're doing. So let's put it down somewhere here. Base spatial, so that we can certainly make it smaller. Here we go. So the error bound, now let's calculate the error bound. The error bound for this will be, as shown here, 2 minus 1, that's 1. 1 to the cube, that's still 1. So we have 1 times 2, obviously. I'm going to write it just so that you know what I'm doing. 1, that will be times 2, divided by 12, divided by 16. So that's the error bound, 0.01, and that would be the maximum error. And definitely we know that we are way below that error. I mean, the error that we got, the truncation error is negative 0.03. So this value here of 0.01 for me doesn't make much sense. I mean, well, let's put it this, it's kind of a maximum bound error that when you apply your formula for n equal 4, but for certainly your truncation error, which is more meaningful, it definitely is going to be smaller, a lot smaller. See, if I divide it, like for example, in the absolute value of this number divided by this, about 3 times smaller the truncation error. That's basically what I'm saying. Wow, good enough. This is, so we calculate the, let's go back and let's summarize what we did on this problem. First question was, let's open this a little bit more. Calculate the truncation error, and we did that using an actual formula. you know, the real formula like this one here, and then the error bound, we use the formula for the error bound, and the truncation error, let's see. Good. We are missing one part here, and I'm going to explain that in a second. What we are missing is, let's see if I can reduce this, is basically we're going to apply the truncation formula, this one here, and we haven't done this yet because we did this value, the negative 0.003 that we saw is actually, if you know the actual integration, the value that come out that you can get from here. But let's say that you don't know that and you still want to get the truncation error. How you do that? Well, that's when you apply this formula here. Okay, we need to apply this. And how we do that? Well, let's get here for a second. There we go. How we apply this formula, and it's kind of interesting because basically if you check what is the average of this second derivative, let's put it right here. Let's say that I'm interested in the average of the second derivative of x. Let's put it in general. Well, no, let's write it like this, of epsilon. That will be the integral of the second derivative of x evaluated between, in this case, between a and b dx divided by b minus a. All right? So this is the average. It's kind of a different, as I told you, it's a different calculation that you need to use. So now let's apply this to our problem. And this is the funny part. Since you are interested in integrating this part here, it's basically like you go back to the integration of the second derivative will be the first one, right? So it will be f of x evaluated between a and b divided by b minus a. So if you remember, let's go back here. This is f of x. The first derivative is this one here, is minus 1 over x squared. That's what we are interested for this part here. So I go pick that integration, minus 1 over x squared. So it's going to be 1 minus x squared, but this need to be evaluated between, in this case, between 1 and 2, and that will be 2 minus 1. That will be, let's write it like this, and now let's do the evaluation. So that would be minus 1 over 4 minus 1. When I'm evaluating on 1, that will be 1 minus 1, and that would be over 1. So if I check this out, that will be negative 0.25 minus, that would be plus 1 divided by 1. So this will be positive 0.75. That's the value that I'm using. Kind of different, right? From the, I think that we got 2 last time for the maximum. Yeah, right here. You see, when we are using the error bound. So in truncation error, I got 0.75. So now let's calculate the truncation error by using formulas. That would be, which is an approximation. That's what I put an A here. So that would be minus b minus a. That would be 2 minus 1 to the cube. I'm going to put everything just so everybody is with me on board on this. Over 12 over n, but n I said that is 4. So that's 4, that's 16. times 0.75, 0.75. And now let's check this out. So that approximate truncation error 2 minus 1, that would be 2 to the cube, that's still 1. So it's simple as 0.75 divided by 12 divided by 16, right? Again, I'm going to take this to Excel. So you see it there. Oh, 1 second until I make this. There we go. So basically, the truncation error, if I write it here, let's say truncation, well, the approximate value of the error in this case for truncation will be minus 75, 0.75 divided by 12 divided by 16, and I got negative 0.0039. Now, this is the part that, as I was telling you guys, makes more sense to use truncation error, because at the end, this is by the formula, what I got, 0.0039. So I don't know the real value of the integral, because let's say that I don't know how to integrate a particular function because it's so complicated that you cannot do it. So, but you still want to have a good idea of the truncation error, what's going to be if you use a certain value of n for the trapezoidal rule. So in that case, like for example, under this formula, n equals 4, I calculate the truncation error is going to be negative 0.00391. Now, if you know how to integrate the, the function that you're working on, you get a value of 0.00388, obviously 0.39. Remember, this is an approximation value, but still it's pretty much right on the money, So that's why I prefer truncation error over error bound. For me, it has more meaning than the total error bound, and so that's what I prefer to use, truncation error. In this exercise, let's go back to OneNote. In this exercise, basically, the n value was given, n equals 4, and we did, as a summary, we did the error bound, maximum error bound, we did the error for truncation error, and we also did the approximation of the truncation error using a formula, and we noticed how close we were between these two. This is based on formula, and this is based on that if you know how to integrate the function that you're working on. Now, again, this is because somebody provided the n value. It's going to be 4. We're going to do now a second exercise, and for this, let me think about it. That would be like, for example, let's use a more complicated number, okay? But the question is different. Okay, let's change here the page. Let's change page. Let's start by having an integral. Let's say that I'm going to be integrating from 0 to 2, something that is a little bit more complicated. Well, it's not that more complicated, but again, I'm saying that you need to do integration by parts if you want to work on this one. And just for the sake of the argument, I'm not doing that here to show you how you can integrate that, but I'm going to give you the result, the final result of that one. If you do that one, that would be 8.3a. Let me open this higher, 8.3905. That will be the actual value of that integral now. And here is the question. What will be the value of n such that we get a truncation error, which is again more meaningful for us, that we get a truncation error of at least less than or equal 0.00001. That's very small. So that's what we are looking. We are looking for a truncation error that be that small. If you remember the formula, what we are saying that we want our ET, you remember this should be by formula minus BA to the cube 12 n squared times the average of the second derivative, and let's do that. So basically, if we wanna work on this such that this value here is less than the value of ET. Okay, we want to, and just to sake of the argument and deal with the negative, let's say that this is less or equal, and for, I'm going to put that positive for 1 second and don't worry about it because I'm looking for absolute value at this point. So that's it. So I'm working on this problem such that n, the value of n, be big enough that when I work all these details, the truncation error, and remember this is by formula, so I should write here EA instead of ET. EA is that 12 n squared, and that will do. Okay, so let's see how we work this out. First of all, the function that we are interested in this case is x e to the x. So we need derivative here, and we need the first one. Which for me would be more than enough. Getting to the second derivative, if I'm only interested in getting the value of n, is not necessary. It's the first derivative that I'm interested, and you know why? Because we're going to be integrating the second derivative, so we're going to go back to the first derivative. You see what I'm saying? So let's work on the first derivative. So we apply the chain rule. That will be the derivative of x, that will be 1 times, we don't mess with the second, plus, now we leave the first in place, but we mess with the second, that will be e to the x, because the derivative of x to the x is e to the x, and the derivative of x with respect to x is 1. So it stays like that. That's the first derivative, so I don't have to do anything else. That will be, I can take e to the x as a factor, and that will be 1 plus x. There's nothing else there. Now, I'm interested in doing an evaluation of this integral. So let me write it like this. This is the average of the second derivative of epsilon equal, if you remember, is the integral of the second derivative. Oops, no average there. Here. Of the second derivative of x with respect to x between the limit, and in this case between a and b. I'm going to write it like this in general, and that divided by b minus a. If I apply that, that will be my first derivative, which is here. This will end up being this one. So basically this is the integral of that, ex 1 plus x, and that's it. Evaluate it now at the limits, which for this integral is between 0 and 2, and that divided by 2 minus 0, that would be 2. So this result will be when it's 2, when x is 2, is e to the 2 times 1 plus 2, that would be 3. I can write this here, minus, obviously, everything over 2, minus when x is 0. When x is 0 is e to the 0, and that e to the 0, and that will be 1. See? So that second derivative, the average of the second derivative, let me put this beautiful here. So that would be 3e squared minus 1 and all that divided by 2. Let me plug that into Excel and let's see what we got. Since this is a new problem, let's change page here. Let's open this big. And let's put this somewhere here. Again, I use bitmap. Since it's coming from one node and sometimes it get kind of messy. That will do. So let's say that the average of the second derivative, I can put that here. The average of the second of this, the average of f double prime equal, and let's do the calculation here, is set that is 3e squared, so that 3 times exponent of 2, all that minus 1, and let's put a parenthesis here, another, close those parentheses, and all that divided by 2, and that's the value. So we get 10.5836 at 4 decimal places. So let me go to one node here and let's put that here. So that value is 10.5836. All right. So with that said, now let's calculate the approximate truncation error, or actually the value of n, which is the one that I'm interested. For this case, n is going to be, let's see. So we have b minus a. Let's do the formula here. b minus a, so that would be 2 minus 1. I'm using this here. 2 minus 0, sorry for that. 2 minus 0, elevated at the cube, divided by 12, n squared, and that has to be multiplied by the average of the second derivative. That would be 10.5836, and that has to be less or equal to 0.0001. Now, need to put this in terms of n squared. So if I put n squared down here and divide by that, you certainly will look more like this. N squared has to be greater than, n squared have to be greater or equal than 2 to the 3, that would be a, divided by 12, and multiplied by 10.5836, and that divided by 0.0001, which is the truncation error that I want. So if I take the square root of all that, n has to be greater or equal than, if you allow me not to write that much, I need that, I will need that. Let's put it somewhere here. So, oh, that's too close. Let me, for comfort, let's get it a little bit. There we go. So I think that I took things that are, let me fix this. There we go. So there we go. So that will be square root of that. That will be the n value that I need for having a truncation of around 0.001. Okay, let me get that to Excel, and let's see what we get in Excel. Just put this here somewhere I can see it. Space spatial bitmap. Here we go. Since I'm coming from OneNote, that's why it looks so big, because it's way amplified at OneNote. So let's see. Okay, so the value of n that I require is, let's put a parenthesis here, that would be a times 10.5a 36. But basically I can use this one, but I'm using the one that I wrote here just because, well, I don't know, let me think about it. Since I'm doing Excel, let's use everything from Excel. So that would be a times this, oops, sorry for this, put the formula here, I forgot, equal now a times this divided by 12 divided by 0.0001, and here all that elevated to the 0.05, and that will do. So, and basically you don't use I mean half of a box, use a full box, so that would be basically 266. Oops, sorry, 266. That's the value of n. N has to be, and finally 266. If you want that precision of 0.0001, and that's at the level of truncation error, we need to get to about 266 trapezium within the trapezoidal rule. How about if we do that? Let's do that, because basically we're gonna do this. I gave you the, if we go back, I gave you the true value of this 8.38905. So in other words, you have this, you know, the real value. So if I gonna calculate the truncation error, I can certainly use 8.38905 less than now than the value, than the area that I got for the trapezium. And now I need to apply 266 steps. Obviously you would never do that by hand. You will use, like, for example, I mean, a program, or it's very easy to do this in Excel. So I'm gonna calculate that AT of the 266, and this difference better be pretty much the same as let's say 0.0001. I mean, because that's what we start with, right? So we're gonna have to end the same that we started. So let's do that. Again, let's say A for our problem is 0, B is 2, the n value is actually 266, no problem there. Now delta x for this problem is b minus a, whoops, so b minus a divided by the number of steps, and that's how small it is, but no problem. X, again, f of x, and we're going to be using trapezoidal rule, and so we start equal to this value here, and so f of x equals, remember, the function now is x times ex. Remember here, the function that we are working obviously is x times e to the x. Okay. All right, let's do that. X times e to the x. Let's go back to Excel and let's do that. It will be x times exponent, that will be multiplied again by it, I mean, sorry, by that's the B11. Close this, and that obviously will be 0. Now here we're gonna be using this plus delta x. Where's the delta x? Right here. Remember to put a $sign so that number is fixed. And now we move sideways. Oh, sorry. No, downward here. There we go. And that's the evaluation of x. Let's see. Let's be sure that everything looks good. Yeah. Now it's as simple as watch here, because we're gonna do this. We gotta hit the 2 here. I mean the two here. So we're gonna go a little bit further on this. We are almost done. If you go over, no big deal. I already did. You know, you step again on the number 2. Let's see, where is it? Right there. See? And then you take all this and clear, so not to get confused. Clear content, and that's it. Now here is the part that you want to apply the trapezium rule. So the first one, there's no, I mean, stay the way it is, but it's the second one that you need to multiply by 2, because those are the one in the middle, and you multiply this by 2. When you do that, you then follow with the others up to almost the end, up to here, because this one just move sideways, and that's it. Now you have all the elements for the your sum here. Let's do that. Let's do the sum now. Oops, here we go here. So my value here will be equal to the sum of all these. You can do Control Shift up if it's a huge table, or you can do like this because it's not that big. And here you end up there, close this, and then multiply that by delta x, which is this one, and divide that by 2. And now you got, that's actually the integral area using the trapezoidal rule. So that would be, let's copy that, let's copy that value and compare that to, let's see where we're gonna get that done. Actually, I can certainly do that right here. Let's write it here as for the time being. And so it's gonna be a paste. Let's say number only. So this is a trapezoidal rule value. The area was that one. Now the analytical result, or the real value, but let's write analytical, or the real value, no problem. Real value, if you remember, that real value was, let's put it here, that was 8.38905. Now if I do the difference between those two values, let me get here, insert, so that I get a little more spaced. So the error, the truncation error for this case will be the real value, which is this one minus this one. Here we go. That's what we get, negative 0.0001. As close as it can get. See, the other one was an approximate value. The one that I got, I mean, using the formula. Let's see, where is it? Did I write it here somewhere? Let's say. Well, actually, never mind. What I was saying is, yes, it ended up being the value that we start with, basically. We said that we want a truncation error that be at this level of precision at 4 decimal places, 1, 2, 3, 4, and that's what we got. All right. Again, I mean, you can certainly use the error bound. I prefer truncation error because it makes more sense to me. At the end, it makes a lot of more sense. I mean, you end up, if you want to have a precision on your integral of this at this level, then you have to have for this particular integral, you have to have a, I mean, 266 step, right? Just to do it right at that precision level. If you change the precision, then the number of like for example, if I can survive, I mean, if I like this integral with a, let's say with 0.01, then obviously this number will be a lot smaller than the 266. All right, so that will do. Thank you for listening, and as I always said, be safe whatever be your final destination. Again, this is just a comparison between error bound and truncation error. And who won on this? I think truncation error did a marvelous job.